k is less than or equal to the index I of node x on its path. So every node belongs to exactly one path. This is a path decomposition. It's a partition of the tree into paths. Not all the edges are represented, but all the nodes are there. All the nodes belong to some path. And so, and we're going to store for every node, store what its index is and where it lives in its array. Okay, so look at that index in the array. If k is less than or equal to that index, then we can solve our problem instantly by looking at the path array at position I minus k. That's what I said before. If our kth ancestor is within the path, then that's where it will be. And that's going to work as long as that is non-negative. When I get to negative, that means it's another path. Okay, so that's the good case. The other case is we're just going to do some recursion, essentially. So we're going to go as high as we can with this path. We're going to look at path array at position 0. Go to the parent of that. Let's suppose every node has a parent pointer. That's easy. Regular tree. And then decrease k by 1 plus I. Okay, so the array let us jump up I steps. That's this part. And then the parent stepped us up one more step. That's just to get to the next path above us. Okay, so how much did this decrease k by? I'd like to say a factor of 2 and get log n, but in fact, no, it's not very good. It doesn't decrease k by very much. It does decrease k, guaranteed by at least 1. So it's definitely linear time. And there's a bad tree, which is this. It's like a grid. Whoa, sorry. Okay, here's a tree. It's a binary tree. And if you set it up right, this is the longest path. And then when you decompose, this is the longest path, and this is the longest path, this is the longest path. If you query here, you'll walk up to here, and then walk up to here, and walk up to here, and walk up to here. So this is a square root of n lower bound for this algorithm. So not a good algorithm yet, but the makings of a good algorithm. Makings of step 3, which is called ladder decomposition. Ladder decomposition is something I haven't really seen anywhere else. I think it comes from the parallel algorithms world in general. Now we're going to achieve linear space log n query. Now this is an improvement. So we have at the moment n log n space log n query or n space root n query. We're basically taking the min of the two. Right, so we're getting linear space log n query. Still not perfect. We want constant query. That's when we'll use indirection, I think. Yeah, basically. A new type of indirection, but okay. So linear space log n query. Well, the idea is just to fix long paths. And it's a crazy idea. Okay, let me tell you the idea, and then it's like, why would that be useful? But it's obvious that it doesn't hurt you. Okay, when we have these paths, sometimes they're long, sometimes they're not long enough. Just take each of these paths and extend them upwards by a factor of 2. That's the idea. Extend, so take number 2, extend each path upward 2x. So that gives us what we call a ladder. Okay, what happens? Well, paths are going to overlap. Fine. Ladders overlap. The original paths don't overlap. Ladders overlap. I don't really care if they overlap. How much space is there? it's still linear space because I'm just doubling everything. So at most doubled space relative to long path decomposition. I didn't mention it explicitly, but long path decomposition is linear space. We're just partitioning up the tree into little pieces. Doesn't take much. We have to store those arrays, but every node appears in exactly one cell here. Now every node will appear in, on average, 2 cells in some weird way. Like, what happens over here? I have no idea. So this guy's length 1. It's going to grow to length 2. This one's length 2, so now it'll grow to length 4. This one's length 3. I mean, it depends how you count. I'm counting nodes here. So it's going to go here all the way to the top. Interesting. And all the others will go to the top. So if I'm here, I walk here, then I can jump all the way to the top, then I can jump all the way to the root. Not totally obvious, but it actually will be log n steps. Let's prove that. This is, again, something we don't really need to know for the final solution, but kind of nice, kind of comforting to know that we've gotten down to log n query. So it's at most double the space. So still linear. Now, there's one catch. Over in this world, we said each, I didn't say it, but I meant to, or I mentioned it out loud. Every node stores what array it lives in. Now a node lives in multiple arrays. Okay, so which one do I store a pointer to? Well, there's one obvious one to store a pointer to. There's whatever node you take lives in one path. In the long path decomposition, it still lives in one path. Store a pointer into that ladder. Okay, so node stores a pointer. You could say to the ladder that contains it in the lower half. That corresponds to the one where it was an actual path. And only one ladder will contain a node in its lower half. The upper half was the extension. I guess it's like those folding ladders you extend. Okay? Cool. So that's what we're going to do, and also store its index in the array. Now we can do exactly this query algorithm, again, except now instead of path it says ladder. So you look at the index of the node in its ladder. If that index is larger than k, then boom, that ladder array will tell you exactly where to go. Otherwise, you go to the top of the ladder, and then you take the parent pointer, and you decrease by this. But now I claim that decrease will be substantial. Why? If I have a node of height h, remember height of a node is the length of the longest path from there downward, it will be on a ladder of height at least 2h. Why? Because if you look at a node of height h, like say, I don't know, this node, it lives, the longest path from there is, substantial. I mean, if it's height h, then the longest path from there is length at least h. So every node of height h will be on a path of length at least h, and from there down. And so you look at the ladder, well, that's going to be double that. So the ladder will be height at least 2h, which means if your query starts at height h, after you do one step of this ladder search, you will get to height at least 2h, and then 4h, and then 8h. And you're increasing your height by a factor of 2 every time. So in log n steps, you will get to wherever you need to go. Okay, you don't have to worry about overshooting, because that's the case when the array tells you exactly where to go. Okay. Time for the climax. This won't be the end, but it's the climax in the middle of the story. So we have, on the one hand, jump pointers. Remember those? Jump pointers made small steps initially and got, actually, no, they made this is what it looks like for the data structure. But if you look at the algorithm, actually it makes a big step in the beginning. Right? It gets more than halfway there. Then it makes smaller and smaller steps, exponentially decreasing steps. Finally, it arrives at the intended node. Ladder decomposition is doing the reverse. If you start at low height, you're going to make very small steps in the beginning. As your height gets bigger, you're going to be making bigger and bigger steps. And then when you jump over your node, you found it instantly. So it's kind of the opposite of jump pointers. So what we're going to do is take jump pointers and add them to ladder decomposition. This is, I guess, version 4. Combine jump pointers from 1 and ladders from 3. Forget about 2. 2 is just a warm-up for 3. Long paths, defined ladders. Okay, so we've got one way to do log n query. We've got another way to do log n query. I combine them, and I get constant query. Because log n plus log n equals 1? I don't know. Yeah. Okay. Here's the idea. On the one hand, jump pointers make a big step and then smaller steps. Or, yeah, like that. And on the other hand, ladders make small steps. It's hard to draw. Okay. What I'd like to do is take this step and this step. That would be good. Only 2 of them. So query is going to do 1 jump plus 1 ladder in that order. See, the thing about ladders is it's really slow in the beginning because your height is small. I really want to get large height. Jump pointers give you large height. The very first step, you get almost half the height you need. That's it. So when we do a jump, we will we do 1 step of the jump algorithm. What do? We reach height at least k over 2 above x. Right? We get halfway there. So our height, it's a little let's say x has height h. Okay, so then we get to height, this is saying we get to height h plus k over 2. Okay, so that's good. This is a big height. Halfway there. I mean, halfway of the remainder after h. Now ladders double your height in every step. So ladder step, so this is the jump step. If you do 1 ladder step, you will reach height double that. So it's at least 2h plus k, which is bigger than what we need. We need h plus k. That's where we're trying to go. And so we're done. Isn't that cool? So this first step gets you, I mean, so the annoying part is, there's this extra part here. This is the h part. And that's, we start at some level. We don't know where. This is x. The worst case is maybe when it's very small, but whatever it is, we do this step. This is our target up here. This is height h plus k. In one step, we get more than halfway there with the jump pointer, and then the ladder will carry us the rest of the way. Because this is a ladder. We basically go horizontally to fall on this ladder, and it will cover us beyond where we need to go, beyond our wildest imaginations. So this is k over 2. Because not only will it double this, which is what we need to double, it will also double whatever's down here, this h part. So it gets us way beyond where we need to go. I mean, it could be h is 0, then it gets us to exactly where we need to go. But then the ladder tells us where to go. So 2 steps, constant time. Now, one annoying thing is we're not done with space. So this is the anticlimax part. It's still going to be pretty interesting. We've got to shave off a log factor in space. But hey, we're experienced. We already did that once today. Question?
Why is it okay to go past your target?
So it's okay. So jump pointer, the question was, why is it okay to go past our target? Jump pointers aren't allowed because they only know how to go up. They can't overshoot. That's why they went less than halfway. Or more than halfway, but less than the full way. Ladder decomposition can go beyond. Because the point is, as soon as here's u, x, and here's your kth ancestor. This is the answer. As soon as you're in a common ladder, then the array tells you where to go. So even though the top of the ladder overshot, there will be a ladder connecting you to that top of the ladder. So as long as it's somewhere in between, it's free. Yeah, so that's why it's okay. This goes potentially too high. So it's good for ladders, not good for jumps, but that's exactly where we have it. Other questions? Yeah.
Jump pointers, wouldn't you be high up enough in the tree so that just long path would work?
Oh, interesting question. So would it be enough to do jump pointers plus long path? My guess is no. So jump pointers get you up to, so think of the case where h is 0. Initially you're at height 0. I think that's going to be a problem. You jump up to height k over 2 with a jump pointer. Now in long path decomposition, you know that the path will have a length at least k over 2, but you need to get up to k. And so you may get stuck in this kind of situation where maybe you're trying to get to the root and you jump to here, but then you have to walk. So I think the long paths aren't enough. You need that factor of 2, which the ladders give you. You can see where ladders come from now, right? I mean, we got up to height k over 2. Now we just need to double it. Hey, we can afford to double every path, but I think we need to. Other questions? Okay. So last thing to do is to shave off this log factor of space. And we're going to do that with indirection, of course, constant time and log n space. But it's not our usual type of indirection. Use this board. Indirection. So last time we did indirection, it was with an array. And that's actually pretty much every indirection we've done, it's been with an array-like thing. We could decompose into groups of size log n, and the top thing was n over log n. So it's kind of clean. This structure is not so clean because it's a tree. How do you decompose a tree into little things at the bottom of size log n and the top thing of size n over log n? Suppose, for example, your tree is a path. Ooh, bad news. Bad news. My tree were a path. Well, I could trim off bottom thing of size log n, but now the rest is of size n minus log n, not n divided by log n. That's bad. I need to shave a factor of log n, not an additive log n. Can you tell me a good thing about a path? I mean, obviously, when we can put it in an array, but can you quantify the goodness or the path-likedness of a tree? Well, I erase this board. It's kind of a vague question, but. Good thing about a path is that it doesn't have very many leaves. That's one way to quantify pathedness. If a small number of leaves, I claim life's not so bad. I actually need to do that before we get to indirection. Step 5 is let's tune jump pointers a bit. I want to make them, so they're the problem, right? That's where we get n log n space. They're the only source of our n log n space. So what I'd like to do is, in this situation where the number of leaves is small, we'll see what small is in a moment, I would like jump pointers to be linear size. Okay, here's the idea. First idea is, let's just store jump pointers from leaves. Okay, so that would imply L log n space, I guess, plus linear overall. instead of n log n, now we just pay for the leaves. Except we kind of messed up our query. First thing query did was at the node follow a jump pointer. But it's not so bad. Here we are at x. There's some leaves down here. And we want to jump up from here, from x. How do I jump up from x? Well, if I could somehow go from x to really any leaf, the ancestors of x that I care about are also ancestors of any leaf descendant of x. So all I need to do is store for each node any leaf descendant. Single pointer. This will be linear. From every node. Okay? So I start at x. I jump down to an arbitrary leaf, say this one. And now, so I have to do a query. Jump down. And let's say I jump down by d. Then my k becomes k plus d. Right? If I went down by d, then and I want to go up by k from my original point, now I have to go up by k plus d. But hey, it's just, we know how to go up from any node that has jump pointers. So now we have a new node, a leaf. So it has a jump pointer, has jump pointers upward. So we follow that one jump pointer to get us halfway there from our new starting point. We follow one ladder thing, and we can get to the level ancestor k plus d from the leaf, and that's the level ancestor k from x. Okay, this is like a reduction to the leaf situation. We really don't have to support queries from arbitrary nodes. Just go down to a leaf and then solve the problem from the leaf. Okay? Okay, so now if the number of leaves is small, my space will get small. How small does L have to be? N divided by log n. Interesting. If I could get the top structure to not have n over log n nodes, that's not possible. I can at best get to n minus log n nodes. If I could get it down to n over log n leaves, that would be enough to make this linear space. And indeed, I can. This is a technique called tree trimming, or I call it that. I don't know if anyone else does. But I think I've called it that in enough papers that we're allowed to call it that. So, boom. It's originally invented by Alstrup and others for a particular data structure. There's many versions of it. We will see other versions in future lectures, but here's the version you need for this problem. Okay, here's the plan. I have a tree. And I want to identify all the maximally deep nodes that have at least log n nodes below them. This will seem weird because we really care about leaves and so on. So, there's stuff hanging off here, whatever. I guess I'm thinking of that as one big tree. No, actually, I'm not. Okay, I do need to separate these out. But one of these nodes could have arbitrarily many children. We have no idea. It's an arbitrary tree. Okay, and what I know is that each of these triangles has size less than quarter log n, because otherwise this node was not maximally deep. Okay, so if this head size is greater than or equal to quarter log n, then that would have been the node where I cut, not this one. So I'm circling the nodes that I cut below, so meaning I cut these edges. Okay, so these things have size less than a quarter log n, but these nodes have at least a quarter log n nodes below them. So how many of these circled nodes are there? Well, at most for n over log n such nodes. Right? Because I can charge this node to at least a quarter log n nodes that disappear in the top structure. So if there's at most, now, but these things become the leaves. Right? If I cut all the edges going down from there, that makes it a leaf. And they're the only leaves. They're the only leaves? Yeah. I mean, if you look at a leaf, then it has size less than a quarter log n. So you will cut above it somewhere. So every old leaf will be down here. And the only new leaves will be the cut nodes. Okay, so we have order n over log n leaves. Ah, yes. Good. So it's funny. We're cutting according to counting nodes, descendants, not leaves. Won't work if you cut with leaves. Cut with nodes. But then the thing that we care about is the number of leaves went down. That will be enough. Great. So up here, we can afford to use 5, the tuned jump pointer combined with ladder structure. Because this only costs L log n. L is now n over log n, so the log n's cancel. So linear space to store the jump pointers from these circled nodes. So if our query is anywhere up here, then we go to a descendant leaf in the top structure, and we can go wherever we need to go. If our query is in one of the little trees at the bottom, which are small, they're only a quarter log n, so we're going to use a lookup table. Either our answer is inside the triangle, in which case we really need to query that structure, or it's up here. If it's up here, we just need to know, basically, if every node down here stores a pointer to the dot above it, then we can first go there, see is that too high? If it's too high, then our answer is in here. If it's not too high, then we just do the corresponding query in structure 5. Okay, so the last remaining thing is to solve a query that stays entirely within a triangle, a bottom structure. And that's where we use lookup tables. Again, things are going to be similar to last time, except for now up to step 7. But it's a little bit messier because instead of arrays, we have trees. And here it's like we graduate from baby combinatorics, which is how many plus or minus 1 strings there are, power of 2, to how many trees are there. Anyone know how many trees on n nodes there are? It's a one-word answer. No. Nice. That is a correct one-word answer. Very good. Not the one I had in mind, but anyone else? Nope. You're thinking n to the n, that would be bad. We could not afford that because log n to the log n is super polynomial. Fortunately, it's not that big. It's roughly 4 to the n. The correct answer, the exact answer is called the nth Catalan number, which didn't tell you much. I didn't write it down, but I'm pretty sure it is 2n prime, choose n prime, 1 over n prime plus 1-ish. Don't quote me on that. It's roughly that. It might be exactly that. Someone with the internet can check. But it is at most 4 to the n prime. So that the computer science answer is 4 to the n, indeed. It's just some asymptotics here. Why is it 4 to the n? 4 to the n you could also write as 2 to the 2n prime, which is, first let's check this is good, and then I'll explain why this is true in a computer science way. So we've got a quarter log n up here. So the 1, 2 cancels with 1, 2 up here. So we have 2 to the half log n. So this is our good friend, root n. Root n is just something that's n to the something, but is n to the something less than 1. So we can afford some log factors. Why are there only 2 to the 2n prime trees? One way to see that is you can encode a tree using 2n bits. If I have an n node tree, I can encode it with 2n bits. How? do an Euler tour. And all you really need to know from an Euler tour to reconstruct the tree is, at each step, did I go down or did I go up? Those are the only things you can do. If you went down, it's to a new child. If you went up, it's to an old node. So if I told you a sequence of bits for every step in the Euler tour, did I go down or did I go up, you can reconstruct the tree. Now, how many bits do I have to do? Well, twice the number of edges in the tree, because the length of an Euler tour is twice the number of edges in the tree. So 2n bits are enough to encode any tree. That's the computer science information theoretic way to prove it. You could also do it from this formula, but then you'd have to know why the formula is correct, and that's messier. Cool. So we're almost done. We have root n possible different structures down here. We've got n over log n of them, or maybe. I don't know. It's a little harder to know exactly how many of them there are, but I don't care. There's only root n different types, and so I only need to store a lookup table for each type. The number of queries is order log squared n again, because our structures are of size order log n. And the answer to a query is, again, order log n bits, because there's only log n different nodes to point to. And so the total space is order root n log n squared log n for the lookup table. And then each of these triangles stores a pointer, or I guess every node in here stores a pointer to what tree we're in, or what type of tree we have, and also what node in that tree we are in. So every guy in here, because that's now part of the query, has to store not only a little bit more specific pointer into this table. It actually tells you what the query part is, or the first part of the query, the node x. Then the table also is parameterized by k. So one of these logs is which node you're querying. The other log is now the value k, but again, you never go up higher than log n. If you went up higher than log n, then you'd be in the 5 structure, and so you just do a query up there. You don't need a query in the bottom. Okay, so there's only that many queries, and so space for this lookup table is little of n again. And so we're dominated by the space for these pointers, and for the space up here, which is linear. So linear space, constant query. Boom. Any questions? I have an open question. Maybe. I think it's open. What if you wanted to do dynamic? 30 seconds of dynamic. For LCA, it's known how to do dynamic LCA with constant operations. The operations are add a leaf. You can add another leaf. Given an edge, subdivide that edge into that, and also the reverse. So I can erase a guy, put the edge back, delete a leaf, those sorts of things. Those operations can all be done in constant time for LCA. What about level ancestor? I have no idea. Maybe we'll work on it today. That's it.